Resolving forces. Example 1. So we have a block that weighs 5 kilograms, which is on a flat smooth surface. It's smooth, so frictional forces don't count, and all of the forces are either horizontal or vertical, which makes problem solving much easier. Now, to calculate the normal reaction force R, we can look at the vertical forces and use Newton's first law of motion. So vertically there is no acceleration, the resultant force will be 0. So taking the upwards direction as positive, we have R minus 5g equals 0. And then solving gives us R is equal to 49 newtons. In the horizontal direction, we can see that this force is greater than this one, so there will be a resultant force, so we will have acceleration. So we need to use Newton's second law to calculate acceleration, taking this direction as positive, so F resultant equals ma. So because this direction is positive, it will be 80 minus 60 for the resultant force, and then the mass is 5 kilograms, and A is what we're trying to work out. And then we can see that the final answer here is positive, which means it will be in the same direction as our originally chosen positive direction. Example 2. We have a 5 kilogram block. It's sat on a flat smooth surface. So far these are the only two forces acting on this block, so we can see by Newton's first law of motion that the upward and downward forces on this block will be balanced, so R is equal to 5g. But there's more to it than this. Now there's a 60 Newton force acting in this direction and an 80 Newton force which is inclined at 30 degrees to the horizontal, which also acts on this block. So is R still equal to 5g? So these two are not the only vertical forces in play now. This 80 Newton force will have a vertical component, so this is no longer true. Let's have a look at this 80 Newton force in isolation from the rest of the diagram and resolve it into its two components, its horizontal and vertical component. So we want to resolve this force into two perpendicular directions, like so, and we have a right angle triangle. The hypotenuse represents the original force. It's always the hypotenuse on the right angle triangle that represents the largest and the original force. Okay, make sure the arrows are pointing in the correct direction. So the original force here, this vector here, takes you from there to there, and the red and blue arrows, if we follow those, do exactly the same. We start here and we end here. We work out the components, basic trigonometry. So we have the hypotenuse, this is the adjacent side, so we have to use the cosine function here, 80 cos 30. This is the opposite side, so we have to use the sine function, 80 sine 30. And both of these values here are smaller than this. In a right angle triangle, the hypotenuse is the longest side, so when we're looking at forces, the largest force is on the hypotenuse. So I have resolved the 80 Newton force into two perpendicular directions, horizontal component, vertical component. Now we can get rid of this 80 Newton force, we don't need to consider that anymore. So we can do this. So now when we look at the vertical forces, we have R and 80 sine 30 both pointing upwards, and 5g, the weight of this block, pointing downwards. So again, using Newton's first law and taking the upwards direction as positive, we know the resultant force vertically will be 0. There's no acceleration vertically. So we have R plus 80 sine 30 minus 5g. All of these forces are balanced, so that equals 0. R is equal to 9 newtons. Now horizontally, taking this as the positive direction, we can use the second law, F equals ma. the resultant force this time, if we take this as the positive direction, will be 80 cos 30 minus 60, that's the resultant, equals the mass 5 times the acceleration, which is what we're after. So solving, the resultant force is 9.282 newtons. It's a positive value, so it's in this direction, so our acceleration will also be in this direction. So A is equal to 1.86 meters per second squared, and this double arrowhead shows the direction of acceleration, because acceleration is a vector, it has magnitude and direction. Example 3, we have a 5 kilogram particle, and it is acted upon by these two forces at these angles to the horizontal, so 45 degrees above the horizontal, 30 degrees below the horizontal. And we're looking at a top-down view, a bird's eye view of this system. So to work out the resultant force on the particle, which is a combination of both of these forces, we will resolve these forces into their horizontal and vertical components. So the 10 Newton force has a horizontal component in this direction of 10 cos 45, and it has a vertical component in this direction of 10 sin 45. And this 8 Newton force has a horizontal component in this direction of 8 cos 30, and it has a vertical component in this direction of 8 sin 30. So horizontally we have 10 cos 45 from this force and 8 cos 30 from this force, giving 14 newtons. And vertically 10 sin 45 and 8 sin 30, but these are in opposite directions. This one has a vertical component in this direction, and this force has a vertical component in this direction, but because I've taken this as the positive sense, then that one's positive, 10 sin 45, and this one will be negative. So we have a horizontal component and a vertical component, and these two can be put into a right angle triangle, and using Pythagoras' theorem we can work out the resultant very easily. So the magnitude of the resultant force is 14.3 newtons, and its direction using basic trigonometry, so tan theta will be the opposite over the adjacent in this right angle triangle, so 12.4 degrees above the horizontal. So here is our resultant force, its magnitude and direction given by the arrow. So we have our 5 kilogram particle, we have the resultant force acting on it and the direction in which it's acting. So the magnitude of the acceleration, which is basically Newton's second law of motion, F equals ma, so the resultant force 14.3 equals the mass 5 kilograms times the acceleration, so the acceleration is 2.87 meters per second squared. So acceleration being a vector will have magnitude and direction. Now the direction does not have to be calculated, it's exactly the same as the resultant force. It will be 12.4 degrees above the horizontal. For practice, try these questions.